Well, hello and welcome to this A2EP webinar on saving energy in manufacturing. This is on steam reticulation. It's the first of a four series of webinars, all designed to help manufacturers improve energy performance and achieve some quick energy savings. Today we'll go through three presentations on best practice and steam reticulation, and we'll have Q&A at the end as always. And we have an excellent panel of experts to take you through this. My name's Jared Leake, and I'm the CEO of the Australian Alliance for Energy Productivity. I'd like to acknowledge also our members and who help us bring this webinar together. We have nearly 100 members within the network for A2EP, and they all share our vision of improving energy productivity and decarbonising manufacturing throughout Australia. So many thanks to our members who help support such webinars. This is the first of four webinar series that we have on saving energy in manufacturing. And we thought this is a great way to lead into our Renewable Heat Conference, which is next month. As most people may know, if you're looking to move to renewable heating technologies, it's quite a large investment. So we thought what better way to reduce that investment cost is to look at saving energy and reducing demand first. So we've come up with these four webinars covering steam reticulation systems, steam boiler optimization, heat recovery, and metering and monitoring. Today, it's all about steam reticulation. And to help me through this webinar today, we have our membership manager from A2EP, Mark Barber, joining us. Mark, it looks like both of us need to update our mugshots to have beards, but no, we won't go through that one. But Mark, you've been doing into energy and resource efficiency game for a long time. Hasn't all this saving of energy stuff been done before?
Thanks, Jared. Wouldn't that be nice if that was the case? But unfortunately, that's not the case. It's interesting to note that in this day and age of industry going down this very exciting path of electrification and in implementation of various innovative approaches to energy productivity and decarbonisation, there's still lots of low-lying fruit in industrial sites, particularly around utilities with compressed air, steam production, hot water, chillers. And that's what this series is meant to address.
And there's always new technologies too, Mark, and there's always new ways and best practice. So let's get in there. Mark, I'll hand over to you to introduce our speakers and let's get through into these presentations.
Great. So we've got three speakers lined up. Chris Fox from FlexiGen, El Sadiq Salim from TLV, and Michael East from GECM, Green Energy and Carbon Management. So kicking off with Chris, first speaker. Chris is the founder of FlexiGen, established in 2017, to deliver solutions that help business reduce greenhouse gas emissions, water use, and waste. Chris's career spans industrial project management, process engineering, and sustainability consulting. He's led some major projects, including a $30 million brew house for Lions West End Brewery. Having worked in Australia, Asia, and West Africa, Chris brings a very global perspective and practical insight into sustainability engineering and project delivery. Over to you, Chris.
Thank you, Mark. Okay. Guys, this is just a little bit of background information on FlexiGen. I went through it in the last presentation. It's more just content for the slides as they are released afterwards. So I'm not going to talk through all this. Again, when I originally started putting this presentation together, I thought about all of the areas where you can make a very efficient and well-designed steam system. But to be honest, my two colleagues here, Michael and El Sadiq, they will do a better job covering this than I will. I know enough to be dangerous, but Michael and El Sadiq are the guys to talk to. I've been around the traps, but these guys are the experts. So again, it's in there for context and in there for kind of reference when the slides are shared afterwards, but I'm not going to talk through all of this. What I wanted to talk about today, given the other panelists, was take a bit more of an industrial focus to some efficiency options for steam networks. And what I mean by that is more maybe some kind of slightly more, I wouldn't say complicated, but slightly more innovative technology that can be used to make steam systems more efficient. The three areas I wanted to talk about were cogeneration, steam recompression, and I will touch just briefly on good practice pipework design, but I'm sure El Sadiq will do that too. But I think that's something that when it comes to efficiency in steam networks, it cannot be emphasized enough. So within that, I've broken cogeneration down into two parts. We've got engines where we recover waste heat, and then the other quite relevant one is back pressure steam turbines. Just on the right, for curiosity, there's a photo of a molten carbonate fuel cell. Pretty interesting piece of technology. Once they bring the price down a little bit, but that's happening. I mean, they've been around for a while, and yeah, but we'll talk about that in a little bit more detail in a sec. Next area, steam recompression. Again, kind of two main areas. We've got mechanical vapor recompression, and we've got ejectors or thermocompressors. And finally, I mentioned the good practice network design already. So starting on what I call the cogen supply side, if you have an engine on site which is producing electricity, there is a pretty good chance, or an almost certain chance, it's producing waste heat. And if you also have a need for steam and you're not collecting that waste heat, it would be worth looking into collecting that waste heat. So we've got a couple of different types of engines which will produce waste heat and do occur in kind of larger industrial applications. It's not exhaustive. There are definitely other technologies out there. However, these are probably the main three. First one's gas turbines. Gas turbines are effectively a form of modified aircraft engine. So they're incredibly reliable. They require very little maintenance. These are obviously really big things for the aircraft industry. When you're on a plane and your engine stops, it's a bit different to when your engine stops when you're in a car. Lot bigger consequences. Because of that, though, there are definitely now fairly small gas turbines available on the market, and I think a few of the members of A2EP are marketing those products. But generally, the majority of turbines are pretty big. Disadvantages and advantages, low maintenance, high reliability, not the best electrical efficiency compared to some of the other technologies. These are approximate, and they will vary from situation to situation, but like a rough electrical efficiency from fuel in to electricity out is around 30%. And in terms of steam, same thing. It all depends on pressure and superheat and so on and so forth. But again, a rough figure would be you could probably produce 40 to 50% steam from the exhaust. And how that's done is you put in it's a big heat exchanger with a fancy name called HRSG. It takes the hot exhaust from the turbine and it raises steam. One of the really interesting things about gas turbines is they don't consume a lot of the oxygen from the air that passes through them. Because they were developed for aircraft, they're more looking for flow rather than complete combustion. So the air the exhaust that comes out of a gas turbine is typically about 18% oxygen still. So what you can do is you can put in a thing called a duct burner, and a duct burner is where you just squirt more fuel into the exhaust. It burns because the exhaust is kind of 300-400 degrees, and it will increase the amount of steam that the HRSG produces. So by having that duct burner and sizing your HRSG correctly, you can have you can vary the proportions of electricity and steam you're making for your process. So if you have a variable process, that can be quite an advantage. Basically, gas turbines and probably all of these systems, they do need to run on a liquid or gaseous fuel that doesn't produce ash or residue, or not much anyway. Otherwise, it will create problems. That I've seen concepts where people are trying to use biomass and things like that to run gas turbines with indirect heating and stuff, and looks really interesting, but I'm not sure anyone's really doing it commercially yet. So yeah. Next one I'd like to talk about is fuel cells. There are heaps of different types of fuel cells, but the one I think that's industrially probably the most significant would be the molten carbonate fuel cell. Amazing thing about fuel cells is they're incredibly electrically efficient. So 50%, even higher sometimes, conversion of input fuel energy to electricity, that's very impressive. And the other very impressive thing is that they make very high temperature waste heat, which means you can make quite a lot of steam at high grade from the heat recovery from a molten carbonate fuel cell. Again, as mentioned, there's a lot of other different types of fuel cells that have all different splits of efficiency. Some have very good electrical efficiency, even higher, but the waste heat's of a lower temperature. So, maybe you can't make steam, and if you need steam in your process, maybe that's not so applicable. The other thing is they're very, very specific in the kind of fuel you can feed them. Almost all fuel cells need hydrogen as the fuel, and that's a disadvantage. Some can take methanol and sometimes ethanol. A lot will take methane, but what's actually going on there is they reform methane into basically CO2 and hydrogen. So it's effectively feeding the fuel cell hydrogen from a chemical process upstream, reforming natural gas. Because they're not they're commercial but not in widespread use, they're also quite expensive. So just something to keep in mind. The cogen systems I'd like to mention is reciprocating engines. Reciprocating engines are kind of a little bit different to the first two. They're technology that's been around a very long time. They're effectively just converted marine diesel engines, and quite inexpensive comparatively, but also quite high maintenance and not nearly as much uptime as the first two technologies, because there's a lot of moving parts. So another upside is they're quite electrically efficient, so better than the gas turbine typically, but the downside is that their waste heat comes out in two streams. We've got one, the exhaust, which you can make steam from, and then there's the cooling of the whole engine itself, which you can really only make hot water, say, up to 95 degrees from. So if you don't have a need for hot water and your site needs steam, that 20% is kind of wasted energy. And similarly to the gas turbine, they need a liquid or gaseous, low ash or low contaminant fuel. So effectively, if you have any of these technologies on site or are considering putting these technologies in for power stability reasons or a whole number of reasons, put in the waste heat recovery, and that will give you efficiency in your steam network because it'll just reduce the demand on your boiler. Next cogen topic I want to talk about is demand side. So this is when we've made the steam already, and we're working out how we want to use the steam as efficiently as possible. And the main technology in this space would be a back pressure turbine. A back pressure turbine is not a lot different to the steam turbines that basically make power from in a coal-fired power station or a nuclear power station for that matter. It basically runs by taking high pressure and sometimes, and more often than not, superheated steam and pulling it through a turbine and taking it out at a lower pressure. The difference between what's done at a power station and what's done in a back pressure turbine is that in a power station they pretty much take the steam pressure on the discharge all the way down to vacuum. And anyone who's done a bit of thermodynamics, which I'm assuming quite a lot of the audience has, understands that pressure and temperature are correlated, and the bigger the difference in temperature in any thermodynamic process, the more efficient it is. So in a power station, they're trying to get as much electricity out as possible. In the case of a back pressure turbine, the goal is a bit different. The goal is to take the discharge pressure to the pressure that your plant needs. So rather than chasing every single bit of electricity, if your plant needs, 10 megawatts of thermal heating as well at 8 bar, the idea would be you come in at the higher pressure than you need, and the back pressure turbine takes it down to 8 bar, and then you feed your process with 8 bar. And in doing that, it's far more efficient than a power plant, because we're not only getting the electricity, but we're getting the heat from the steam too. So in terms of trying to find an opportunity for a back pressure turbine, look for any large pressure reducing station, any large pressure reducing valve. They're often or almost always installed in parallel with the pressure reducing station. What that does is it gives you the ability to basically control how much power you want out of the turbine. So if your electrical needs are lower than the output of the turbine, then part of the steam flow goes through the turbine and part goes through the PRV, and so on and so forth. And you just have a control valve which will divert steam either way based on your process needs. Another really interesting thing is they can be quite easily coupled with a condensing turbine, which is the power station thing I mentioned earlier. They literally just put the condensing turbine on one side of the shaft and the back pressure turbine on the other side of the shaft, and both of them feed the generator. So single shaft, one generator. And again, that just gives you incredible flexibility in terms of how much electricity and how much process steam you want out of the system. So if you only want electricity, everything goes through the condensing turbine. If you want a mixture of both, then your control valves will just figure out what's the best balance to suit the load of the plant. These are very much dependent on delta P, and I think the most important thing to take out of this slide is that the availability of smaller turbines and turbines that can take saturated steam at lower pressures rather than superheated high pressure steam has changed a lot in the last 10 years. So there are commercialized units on the market that are out there now. So last thing, steam recompression. Really two types. We've got mechanical vapor recompression, which I think has been talked about in a lot of previous A2EP webinars. So I think most of the audience would know what they are. Pros and cons, they've got good turn down, they've got moving parts, so they need maintenance, and they cost a bit more. I think something that's not been touched on in A2EP presentations previously is thermal vapor recompression. Basically, you can use a device called a thermocompressor or an ejector to compress steam vapor. It will do it with any gas, basically. It takes a higher pressure motive input and a lower pressure or even vacuum input and discharges an intermediate pressure gas from there. And in a steam system, these are regularly used to create vacuums. They're regularly used to kind of compress a low-grade steam to bring it up to a temperature where it's reusable again. Big advantage of these guys is they're no moving parts. They're quite inexpensive. They have very poor turn down compared to an MVR, but because they're cheap, you can manage turn down by having a series of different size units which switch on and off in stages, and effectively similar to the back pressure turbine. Look for places where you've got a big pressure reducing station, and then look for another place where you have a source of kind of low-grade steam or even hot water, which if you put a vacuum on, you could turn into kind of medium pressure steam for a heating process. And in a situation like that, the compression's pretty much for free. Potential applications, any process where you're boiling something. I worked at the Tui's Brewery for quite a while when I was a young engineer. We had a big mechanical vapor recompressor on the kettles there. They were just boiling beer at atmospheric pressure. We took all that waste steam, put it through a 375 kilowatt Roots type blower. And once the kettle was boiling, that blower was compressing the atmospheric steam to a high enough pressure and temperature to actually maintain the boil of the kettle. So as soon as the kettle started boiling, the steam supply was switched off and it was run electrically. And it had a COP of maybe 11 or 12. Some pretty big COP. Also hot water to steam, flash steam, steam purging, and a lot more. And lastly, I'll go through this pretty quickly because I know El Sadiq and Michael will probably talk about it. But the biggest thing in my experience in terms of designing an efficient and reliable steam network is keep condensate, and for that matter, any particulates that shouldn't be there, out of the network. Gas and liquid flow safe velocities are very different. So a safe velocity for gas can be as high as 30 meters per second. Safe flow for liquids like 5 meters per second. So if you have two-phase flow caused by condensate forming in your steam system, you're going to be sending condensate at 30 meters a second, which is a lot denser and heavier than the steam, and it's going to hit stuff hard, and that causes problems over time. Flooded heat exchangers don't transfer heat. So if your steam traps aren't working and your heat exchanger is half full of condensate because it's not getting away, you've lost half your heat transfer area. Your heat exchanger is only going to give you half of the heating it should. All takeoff pipes from steam lines, it's actually the same with refrigeration systems, like with ammonia. Basically, you need to separate the gas from the liquid. All steam takeoff lines should be vertical, point upwards to avoid carryover into the user. Insulation minimizes condensate, so the more insulation you have, the less condensate you have to deal with. And also condensate traps and drains should be regular to make sure it gets out before it ends up in your process. And the picture on the right here, that's just from one of our clients who's dealt with these issues. That's basically a cracked dimple jacket. It's unrepairable. That vessel and another one just like it, basically are irreparable. So in terms of the damage they've done to those jackets, they're going to have to replace both those vessels, and that's not an inexpensive job. So yeah. I've probably gone over time, so I'm not going to go through any of the last two slides again. They're just more for context about our company and for the kind of the slides sent out afterwards. So guys, thank you for your time, and my apologies if I've gone over time a little bit. Pardon me.
Apologies. Thank you for that fascinating tour, Chris. Over to Elsa now. Elsa is a consulting engineer with TLV International, responsible for improving the efficiency, reliability, and productivity of steam users across the globe. Elsa has conducted steam system surveys in 8 different countries, helping to reduce emissions and adapting to local differences. Recently, Elsa completed a round of surveys in Australia and New Zealand to promote steam system optimization, particularly in the food and beverage plants. And I think you're going to talk about some of that work now, Elsa. Over to you.
Thank you very much. Good to see you all. Good afternoon. As mentioned, my name is El Sadiq. So I work for TLV International here. We're more commonly known for the steam traps, valves, etc. we produce, but what I'd like to talk about today in particular is data that we've collected, the data analysis we've done, in particular around steam trap management and steam trap systems. Thank you very much, Chris, because that was a really nice segue talking about the problems with not draining condensate onto now steam trap management.
Pleasure.
Commonly, first of all, when we talk about steam trap management, there needs to be a clear idea of why. When we visit sites, an image like that image there on the right hand side is quite common. You know, flash steam kind of losses from the system. Usually it's okay. But nowadays, thankfully, a lot of manufacturing sites, they're growing, they're expanding. They might use different contractors, and we eventually get to a point where the system's a bit out of control. You've got all sorts of different parts added, so they need a steam trap survey. And on site, they decide, yeah, let's get a steam trap survey to get really on top of our process and understand where our steam traps are and what their status is. Following that, you might have had one yourselves. You get a long list, maybe 200, 300 rows with this steam trap's failed, this steam trap's good, etc. And it can be quite overwhelming to tackle that and to start to maintain replacements. So typically on site, they'll pick and choose, the larger leaks, they'll replace them, or the critical locations, they'll replace them to try and get maximum return on investment. From our experience, often this does not give the maximum savings and it does not give the savings that site initially think they would, but nevertheless, they've ticked that box, they've had the steam trap survey, which is good. And then, the natural decision is that we don't need to get another one for another few years. And then the cycle repeats itself. That's a common situation, and what it leads to images like this. The difference between the top image and this second image is that the second image is a live steam loss. So this is not steam from your condensate system. This is steam from your steam system. So direct, you'll feel that basically on your gas bills, on your boiler directly. But even more scary, in my opinion, are the water hammer issues, and that's if you don't manage to get that condensate out of your system from failed cold, blocked up steam traps. There's one mechanism of water hammer demonstrated there. The results can look something like this. This is a BP oil refinery in 2002. I've been to, I think, at least 2 sites that have had similar rupture incidents like this one due to water hammer, so it's still common in this day and age. Best case, it will result in a shutdown of an entire plant. Worst case, of course, is fatalities and injuries, which does happen. So the proposed improvement, it can seem quite obvious. We'll give a couple cases implemented, but the proposal is something called steam trap management. And again, these might seem quite obvious, but I'll just talk through a non-exhaustive list of what the key principles are of proper steam trap management. First and foremost is smart scheduling. So if you've got, X number of steam traps on site, and you have an annual survey every year, April 20th, you might not catch all of those steam traps on that survey, or some steam traps will be on a irregular load. We typically have a winter load and a summer load, so you want to make sure that you schedule such that every steam trap is tested consistently and at least once every year. Next is to make sure that you can support sites. So you have a steam trap inspection company that's dedicated to supporting you with the implementation and replacements. So one way some companies they can offer, for example, on a map, plot all of your failed steam traps on a map so that it's easy to find where are the problem locations, where can we start making our replacements so that we can drive that failure rate down. Often, like-for-like replacements are favored. Again, it can seem obvious, but making sure that you're replacing based on the application rather than the steam trap that was already there. If we always replace the steam trap that fails every year, then it's going to continue to fail every year. But next, this is some of the key innovations is really looking deeper into the analysis. So if you start having 3 years, 4 years, a steam trap survey data for certain locations, you can get some key insights, which the case studies on the next couple of slides will show. And then finally as well, specialist inspections. There's a term we use at TLV quite often called a CDL. That's a condensate discharge location. And that's that mindset of if a steam trap's not there, it can still be tested as a steam trap location. So a steam trap should be in a location, for example, and also taking into account any leaks and failures that could be as a result of bypass valves and such like that. So whether you conduct your own steam trap inspection or another company, do make sure that the bypass valves are included in the analysis as well. And that gives you your whole condensate discharge location kind of inspection. There are some indicative numbers there in US dollars, but the next slides will show some case studies. So as I mentioned, we're promoting it or trialing this right now in Australia and New Zealand region. This is one site that has adopted it since 2021. So they've adopted those principles as on the previous slide. Their fuel savings to date is about 185,000 Australian dollars. The next slide will talk about the costs associated with that as well, but I just wanted to highlight here, note that these are surveys between 2021 and 2024. They've had 10 surveys, meaning that, again, they've looked at their production schedule and worked with their inspection company to make sure that every steam trap is able to be tested. Then they follow that trend of getting the failure rate down below 10%. And then one case study on the right there on that site of why that repeat testing is so important. So they had a repeat failure on the steam distribution header. And because that's a repeat failure, and even with the replacements, they keep saying it, by looking through the data, it triggered an investigation onto their water system. They found there were some major issues there. They did an upgrade and that resulted in massive water savings as well as steam and water quality improvement on site. So something as small as a steam trap can have wider implications is a key point there that you only find if you do consistent repeated testing and inspection of the steam traps. To talk about the costs now, this is another site, a leading food ingredient manufacturer in New Zealand. This is a simulation we put together based off the data we've collected globally on the typical trend for steam trap management. So you can see the red bar on the left-hand side at year 0. That's their steam trap leakage losses today. And the other 2 bars, the blue and I'm a bit colorblind, green, orange, the other color in the middle there, that's what they're paying now for steam trap replacements and for steam trap surveys. So massive leakage losses. But after implementing steam trap management, first year has typically high costs because then you're replacing a lot of steam traps with typically upgraded models, and the survey costs typically also, they'll hurt you a bit because they're now covering all of the steam traps in detail. However, you can already start to see the leakage losses, that red bar, decreasing massively. And then year on year, you end up with a net benefit. So that's taking into account the cost of a survey, net benefit on this site of well over $500,000 New Zealand dollars. So that's just to highlight that kind of simulation and the kind of general over 5-year plan, the kind of benefits as well as the costs you can see on the y-axis there. But there are further limitations to annual steam trap testing. Even if it's consistent, there may be some further issues that can occur. So let's give a case here where that same site, that food ingredient manufacturer, had 2% failure, very, very low failure, but at critical steam trap locations. So that comes up to about 10 steam traps, let's say. Critical locations have failed right after their 2nd year steam trap survey. Based on calculations, after 1 month, those 10 steam traps have cost about $6,000. 3 months, just under $20,000. And just before their next survey, they've already lost $70,000 over just that 2% failure, just those critical steam traps with large leakage losses. To put in other terms, in terms of emissions, that's 164 tons of CO2 equivalent, 10 steam traps equivalent of the energy that 20 homes would use, equivalent to the emissions of 20 homes. So it's quite sad when you look at it like that, 10 steam traps. So there needs to be some solution for these critical locations that we cannot afford to leave for a full year. Those critical locations as well, more painful can be if we get a process abnormality. So if you've got a jacketed kettle or some cooker, you won't notice a failed steam trap, but you'll notice the uneven heating on your batch process, and you might need to dump that batch. So on site, we take countermeasures. We open a bypass valve, or we blow down the system to make sure that the heating efficiency can still go on. This is an example of a steam trap issue affecting your process massively. And typical solutions are monitoring, as I've been talking about this whole presentation with regards to regular surveys. So you can monitor the steam traps annually. However, what you miss out on are these critical applications where you can't afford to leave it switched off or leaking for the full year. So the solution in this case is an upgrade onto continuous monitoring, which I'll just touch on briefly due to time. But this is where you have basically a non-stop, a continuous steam trap inspection device on critical locations. Not all of the steam traps on site, but areas you highlight to have a very high leakage cost, a very high emissions factor, or where they're attached to process heaters and process applications that you cannot afford to have shut down. And from this continuous monitoring, you are able to predict and put together mechanisms to predict when those steam traps will fail so that you can prevent unplanned shutdowns. And the general outcome is a very, very happy site and production stable. So just to summarize, why steam trap management? We know steam traps, they affect your whole plant. They're like part of your body. You wouldn't go get a health check and not check, the whole body. Steam traps are very critical for that. Regular inspection is critical for that. Plant health cannot be ignored for more than a few years and expect a healthy plant. Best practice replacements will always be better than like-for-like replacements, and have hope that your repeat failures, if any, can be eliminated, and critical applications as well can be managed. Thank you very much for your time. I look forward to the Q&A later.
Fascinating stuff. Thank you, Elsa. Our third and final speaker is Michael East. Michael brings many years of very solid experience in industrial energy efficiency and carbon management, and with a strong focus on delivering client-centric engineered solutions. He helps clients navigate the complex landscape of technologies and equipment to find best fit solutions. His expertise spans compressed air, refrigeration, and boilers, with an increasing emphasis on integrating these into broader carbon strategies. Over to you, Michael.
Great, thank you, Mark, and thanks, Chris and Elsa as well. I learned a few things along the way there, and gave me some ideas to keep an eye out for clients as well. So the portion of the system that I'm looking at, the steam reticulation, is the thermal losses, the insulation piece, and I've called this filling the gaps, and hopefully that message comes through as we roll on. Just really briefly, who are GECM? We're a young engineering consultancy business. We actually just turned 3 a couple of weeks ago. Within the core team, we've got over 40 years of experience in industrial energy and carbon management. So we help our clients with their net zero ambitions, whether that's generation of strategy or what I like to call the practical advice, the energy audits, the developing projects, project implementation, carbon accounting, that actually builds up to support that strategy and implement it. So why insulation? I was just reflecting on what Chris started with there, and that was actually more detailed and more exciting than what I was anticipating. No offense, Chris. I wasn't not downplaying what you put forward there, but the topic that I've got here, insulation. Let's face it, it's one of the least interesting areas. People are nowadays thinking about, okay, what heat pump are we putting in? What are we doing with concentrated solar thermal or an ETES, or how are we managing an electric and a gas boiler side by side and playing the demand and response game. Insulation is not one of those exciting topics, but it's important. And if we have a look at the table on the side there, this is a traditional steam boiler system. Chris sort of alluded to this at the start, and Elsadik has touched on it as well with the condensate losses and flash steam. But a traditional steam boiler system could only be 50 or 60% efficient. And up to 25% of the system losses could be from a lack of thermal insulation. And then I might hear some of you say, well, okay, but I've got decarbonisation plans. I'm going to be changing to a heat pump, or I'm going to be changing to an electric boiler. The thermal losses on the distribution and the demand side that we're talking about are energy source agnostic. It doesn't matter whether that's coming from electricity or hydrogen or natural gas or LPG. So it's an important area to look at from a cost point of view. And if you're still running a fossil fuel system, then it covers your carbon as well. If you are looking at decarbonisation plans, and maybe you're going to convert your boiler at end of life, and that's 5-6 years away, and you're doing the planning now, doing the insulation and other demand side measures can minimize your capital on that supply side. So the thermal insulation, I like to think of it as a decarbonisation stepping stone, because you can either use it to optimize what your system's going to look like moving forwards, or it can be one of those activities that you use to demonstrate some quick wins, get management on board, start to drive the business towards those bigger decarbonisation goals. And once you've got your renewably powered thermal energy source, how are you maintaining that at best practice? That's what the thermal insulation is then about, keeping it at optimum efficiency and keeping your costs as low as possible. So your insulation system, your thermal system's already got insulation. Yes, most pipelines are well insulated. There are some where it's been removed for inspections, but what I'm talking about, as I said, filling the gaps. The areas that we've seen that there's opportunities is your control valves, flanges, strainers, separators. Where you're using the steam, you might have a cooking appliance or a direct injection process, and that you've got an odd-shaped piece of processing equipment, and the shell of that is radiating the heat from the steam inside. So what you can see here in the picture is a fairly common steam manifold, nicely insulated pipes on the top. But when we look at that with the thermal imaging camera, you can see those valves 174 degrees. Very obvious that there's a lot of heat coming from those. Likewise, with this strange flexible coupling, you've got some rigid piping at the end that's got insulation on it, but this flexible union is a little bit tricky to put cladding on or wrap around insulation, but it's 172 degrees. This one's actually installed in a refrigerated plant, So you've got the thermal energy coming through the fossil fuel system that you're paying for once, and then you're paying for it again for the refrigeration unit to use the electricity to take it out of the room again. I spend a lot of time in ceiling cavities. I spend a lot of time on the weekends thinking about being in ceiling cavities. And one of the things I see is, unlabeled pipes like we've got here. Again, a little bit of technology with a thermal imaging camera, and straight away you can see, right, there's one of these that needs some work. Another good example of well-insulated piping. But we've got our friend here, the common flange in the middle, who's sitting there at 171 degrees. So these gaps in the insulation, people think that they've ticked off the insulation box. We did it years ago. It's done and dusted. No need to address it again. What we've seen is that anywhere between about 2% and up to 30% of the system is going in thermal losses in these gaps in the insulation. And the average is about 13-14%. So what does the solution for that look like? So a lot of the reason why they're not insulated is they're odd-shaped components, or you're putting rigid cladding on. You can't just go straight over the top of a flange. So what we found is, probably 95% of the time, the solution is a flexible jacket like these in the examples. So you can have them that are, a fairly standard size to go around your nominal, say, 4-inch valve, but you can also make them to be very bespoke and designed for exactly that, one and only application, like in the middle there where we've got the end of a drum on a boiler, and we've designed the jacket so you've still got the sight glasses sticking out and exposed, so you still meet all your boiler regulations and requirements, but we've cut down on the thermal losses coming out of there. So the other great benefit is that they're easily removable. So valves where you need to do regular inspections, or you want to check for steam leaks on your flanges, etc., you can simply, undo the Velcro straps or the D shackles, take the jacket off, have a quick look, put it back on again. Same thing with your steam traps. If you've put some jackets on some steam traps and you want to do your steam trap survey, we're actually looking at designing some at the moment where you can just undo the flap, test your steam trap to determine if it's working on it, and then do the flap back up. So you don't even have to take the jacket off entirely. The way that we look at this sort of process is we go through the entire site with the thermal imaging camera, and we'll end up with a line-by-line list of, these are your flanges, valves, etc. This is the thermal loss associated with each line item and the cost to insulate each line item. So you can very quickly work out, okay, how can I fit this project into either my capital limitations or make it fit the financial criteria. You might have some, 40, 50 degree hot water that needs insulation, but it's going to have a slightly longer payback. And if you want to control that to 2 years, you might want to cut out that hot water piece. We prefer to group the whole lot together, but it does give you that flexibility to be able to fit in with financial limitations. So what does that start to look like when you pull it all together into the project? Here you can see some before and after shots of a main header manifold in the corner of a boiler house. So beforehand, we've got temperatures there on those valves at about 184 degrees. With the jackets on afterwards, that temperature has dropped right down to 76. And more importantly, the surface area that's at that high temperature is greatly reduced. It's now just the areas where the spindle's going into the valve and the very edge of the jackets. Much of the rest of that jacket surface is way down at 20 odd degrees. I've put some case studies there from real projects that we've done, and I've given a few different examples with, red meat facility, for example, and the small food and beverage, because the way that the sites use steam can be very different. The food meat facility, they've got a large thermal load, going into cookers and render vessels, etc. So the utilization of equipment is quite high. So your percentage losses overall are always going to be smaller. Whereas the food and beverage plant, where they've got steam distributed at multiple points and they're only running one part 3 days a week and another part another few days a week, naturally the percentage losses is higher. You've got a lot more standing losses across the entire system. So the percentage that can be saved from this can vary depending on the type of plant that you are. As I said, average that we've seen so far is around the 13-14%. The really interesting part, though, is the simple payback line there. I think, Mark, you mentioned at the start, there's still low-hanging fruit out there, and I genuinely believe that this is probably one of the easiest to recapture when we've got paybacks in the order of 1 to 1.5 years. Yes, the red meat factory there is at 2.3 years. This was actually done when their gas price was about $10 per gigajoule, so that's gone up about 40-45% since then. So that changes this this simple payback, but it's still very low hanging fruit. The other benefits that we've seen from implementing a number of these projects, it's actually in this particular boiler house example. One of the operators said they want to set up a desk in the boiler house because in summer there's enough cross flow ventilation that it's not absurdly hot, and in winter there's still just enough losses that it keeps you nice and warm. So overall, it's averaged out to be a much more comfortable boiler house than what it was, and you can actually stand on the second level of the boilers for more than 5 minutes without sweating. So to summarize, is it worth reassessing your insulation? And I think the answer is yes, but I think more importantly, it should be, can you reassess your perception of the insulation system rather than thinking, yep, insulation, tick, done it, move on. Gas prices have moved significantly over the last 10 years. And this, I think, is an area where there's, everyone walks past these valves every day. They don't necessarily stop and think about, hang on, how much am I losing from these? How can it be recaptured? And get some of those other benefits as well. So, you can use it to take the edge off your carbon emissions, or use it as you can see there, the low cost of abatement, negative cost of abatement. Use this as a stepping stone on your decarbonisation pathway to justify some decarbonisation activities that might have a higher cost of abatement and balance them out to achieve a better result for your business in a commercially viable fashion. So I challenge you to go away and reassess your insulation and see if it's worth going through there with an infrared camera to find those heat losses. Thank you.
Thanks, Michael. And of course, there's a safety aspect too, isn't there?
Yes, absolutely. I don't usually like to touch on that one because, well, it's all hot surfaces, so no one likes to touch on it. But yes, most of these applications are at sort of the height where you're heading up a staircase and the piping's just next to you. So are you grabbing a handrail or a hot steam pipe? Usually not quite that extreme, but yep, you do get those benefits of personal protection.
And I'll say, Michael, I've been to many plants around Australia, and I was actually trying to work out which one those photos were from. And then I realized, yeah, they all look very similar, and they all look just like that without the valve cozy on there. Maybe put that to the panel, Chris, Sadiq. What percentage of valves and things do you see out there that actually have these coverage? I'm going to call it certainly less than 50 from what I've seen in different factories.
I would say even less, and even the factories that do have insulation over the valves, if it's permanent insulation, as soon as they have a problem with the valve, it's ripped off and it's never put back on again.
Yep.
I'm actually looking at an application at the moment where they do have the sheet metal boxes with insulation around valves. Every 2 years when it's valve inspection time, they cut those off, put them in landfill, and rebuild a whole new rigid valve cover.
Wow.
Best as well. Sadiq, do you visit many plants? How many would you comment on that? On how many have these installed?
It's rare, and like it's very common pictures that you shared, Michael. Even globally as well, most of the plants I've visited are in the UK, and again, some of them, really good insulation practices. But as you said, it's always, happens to be the massive valves, the steam distribution, isolation valves, losing so much heat out of them.
Yeah.
Yeah.
And so often we hear about boiler, when you talk about efficiency, everyone just goes straight to the boiler. And that's going to be 80% without an economizer, maybe 83%. We just don't talk enough about the whole steam system. And what you're presenting there, Michael, when you start putting the steam system down at maybe 70% or so efficiency, you're like, wow, this is a lot of waste heat.
Yeah, I think the best steam system you can have is no steam system.
There it is.
There was a fair bit of discussion in those presentations about the importance of keeping condensate out of the steam system. But Chris, you mentioned in your first slide that condensate is liquid gold. Does the panel want to talk about why it's liquid gold
Well,
and the importance of not wasting the condensate under the ground?
you don't want it in the areas where you need to have steam, but you want it back because it's pure hot water which doesn't need as much treatment going back to the boiler. So it's not that you don't want it, it's more that you want it back in your condensate tank, not in your vessel jackets and not in your heat exchangers. So
Yeah, you've already put the chemicals into it to clean it up, and then you've put the energy into it to get it to hot, and it's just fallen off the edge of being steam.
Yeah.
So it's yes, so close to being steam that you might as well capture it, turn it back into it.
Just
We had a question there from panel to panel there, Michael. Have you seen these valve cozies used in refrigeration plants to stop icing up things?
Yes, the payback is longer, but yes, you can use it on chilled water glycol cooling systems as well. Absolutely.
So Michael, sorry, this is also internal panel question because it was my question. Have you done that analysis based on just the heat losses or the time it would take like a refrigeration mechanic to de-ice a valve before he can work on it and everything like that?
Yeah, so I suppose I am selfish. I live entirely in the energy space. All those calculations are based purely on energy losses, and the funny thing with icing up is it sort of forms its own insulation to a degree to reduce the losses. So,
but yeah, I mean, at the same time, if something goes majorly wrong and the factory's not making any product and it takes them 4 or 5 hours to de-ice the valve before they can do anything to it, it's a big deal potentially.
Yeah, a jacket you'd be able to get off in less than 10 seconds.
Yeah.
Question here from our good friend Alan Pears about the impact of air movement and conduction along pipes. And Michael, have you seen much of impact of that? And yeah, you mentioned about some losses in meat plant, maybe not as bad as for some other when you got longer pipe runs. So
yeah, so
pipes are outside, lots of wind and things.
Yep. So when we do our analysis, we do as I said, line item it, and we also look at is it internal, external, sheltered? Is it exposed to high winds, low level winds, etc. And also what the average ambient temperature is for that region. So if we're doing this in northern Queensland versus down in Victoria or Tasmania, we take all of that into account.
Good.
We've got a question here in Q&A for Chris. Reads, in general, Chris, do breweries across Australia generally have a lot of energy loss, or have they become quite energy efficient over recent years?
It's a really nuanced question. I think big breweries that are built on proper budgets these days are very energy efficient when they're commissioned, and then that fades over time. So as things change, as things get modified, as insulation's removed to access for maintenance reasons and never replaced, things start going downhill. When steam traps stop working properly, and there's there's two ways the steam trap can fail, right? It can either pass steam, and that's something no one will notice unless you do an audit. And if it's passing steam, you're just throwing energy into the wind. The other way is, it'll block and you'll flood a heat exchanger and people will notice straight away because the process isn't working. But yeah, as plants age, if they're not audited and maintained properly, they just continuously go downhill. It's the same thing with compressed air systems, everything. Yeah.
Exactly. I think that point was well made by LCD because that need for maintenance and usually say if you've got an efficient compressed air system, just wait. Give it time and it won't be. It always seems to go off track. Good. This sounds great. I think we can just about wrap it up there. Mark, any more questions to look at before we close things out?
I wouldn't mind asking another question to Elsa, if I may. Elsa, you touched on the importance of not just replacing like for like when it comes to when you found a faulty trap. Can you talk more about is it just a case of replacing the trap component itself, or do you also find that maybe the pipe configuration around that trap needs to be upgraded in some way?
Yeah, very much so. I mean, when we're talking about the steam trap technology itself, we've got a few different types, and some types, like some of the thermodynamic types, especially where you've got them on line drainage. If you've got hundreds of them on site, each of them have a massive standing leakage when they're brand new. So if you've got so many of them, then you're already losing when it's working well, let alone when it starts to leak. So the more typical cases when it comes to like recovering leakage losses is, replacing the models with a high leakage rate in applications where you might have hundreds of them with the more tight sealing models so that you don't have as much leakage. But you're absolutely right in the sense that we look at the whole, or in general, you should be looking at the whole, this condensate discharge location, valves next to it is very, not so common, but it's quite common. We do see bypass valves or blow down valves often open because the people they're opening them are responsible for their kettle, they're responsible for their heat exchanger. So if they see the set points being missed, they'll open that blow down valve, etc. Which is often not picked up until someone goes around and they do an inspection in that steam trap.
Brilliant. Good one.
Thank you.
Thank you so much, Chris, Sadiq, and Michael. Excellent presentations, and we will get those out and distributed shortly. Just to finish off now, let everybody know what's upcoming. So this was the first of 4 webinars. Next week, we're going to be looking at heat recovery. After that, steam boiler optimization, and then metering and monitoring. And so look out for those webinars coming up. We've also got a member mixer and member update coming on the 24th of July down in Melbourne. So please do register for that. And we have the Australian Renewable Heat Conference coming up at the end of August. Fabulous location. We're going to have, we're looking for about 300 or so people there. We've got nearly all 50 presenters locked in, and the content is going to be absolutely fabulous. So really hope you can join us there. Couple of little announcements to make as well. It's great to see the Victorian government come out with their Energy Innovation Fund. They've got $10 million to support electrification, mainly in food and beverage and other manufacturing. So that's going to go a long way to reducing gas usage and decarbonising down to Victoria. And the New South Wales government, not far behind with supporting with these studies. They've got $1 million or so to hand out for various studies, and A2EP has been instrumental in helping them develop such programs. So we'll be looking forward to support members get lots of those grants there as well. If you want more A2EP, follow us on LinkedIn or subscribe to our e-news on our website. But otherwise, all that's left to say is thank you very much for joining us. I hope you have a very pleasant afternoon. And Mark, thanks very much for helping the co-host. We'll see you next time.
Thanks.